in joules. So when we have a change in energy, that is one of our definitions of work, change in energy. So that would look like that. And remember, when we have the change in something, that's like your final minus initial, just to remind you of that. And then work is also defined as the product of force and distance. And product means multiply, so work is also force times distance. If you're holding a 30 kilogram weight at a height of 1.5 meters, I'm using energy, therefore, however, the work is not being done on the weight, it's being done on my muscles. Think of it like this: though I am exerting a force on the weight, its distance moved is 0, therefore there's no work actually being done. So in our first example, if you're actually lifting the weight off the ground, there's a height and a mass, then there is going to be work done on this weight. So here's my weight of 30 kilograms. And we've got a force applied. And then we also have the force of gravity working on that weight. Put this weight up at a constant velocity, you're not accelerating or anything. So your force applied and force of gravity will be the same. So when we do work, it's going to be force times distance, and it will be our force of gravity times distance. Mass times gravity times the distance. So our mass is the 30 kilograms times 9.8 times 1.5 meters. So the amount of work being done on this weight is 440 joules. So we've got the formula. So when you're working against gravity, which is what you were doing lifting up that weight, you're lifting it off the ground, you're forcing yourself to lift it against gravity. Your formula was force times distance, and now we can say that our formula would be mass times gravity times the distance of where it's being lifted. So M is the mass, which is measured in kilograms. And G is our acceleration due to gravity, or you can think of it as just 9.8 meters per second squared. And then the height, or the distance of the object being lifted up, measured in meters. The next one is a 10 kilogram pumpkin is moved horizontally 5.0 meters at a constant velocity. So we've got our mass and velocity is constant, and we've got horizontal distance. And it's moving across a level floor using a horizontal force of 3.0 newtons. How much work is done in moving the pumpkin? So here's our pumpkin here. Let's draw the free body diagram with it. So we've got a force applied of 3 newtons. We probably have some force of friction, but because it's a constant velocity, that means that the force of friction and force applied will be equal. We probably have a normal force and a force of gravity, but those things would cancel out if we were to write out all of these as a net force. Now when we're going to do work on this pumpkin, and it's going to be force times distance, because it's moving horizontally, so the last example was vertical, it was being lifted up. This one is being pushed horizontally, then we use our applied force. So we'll do applied force times our distance. So that would be 3.0 newtons times the distance for the pumpkin, which is 5 meters. So it's about 15 joules of work acting on it. And we used applied force, not the net force. And that's important. So we've got a 3 kilogram pineapple that's held 1.2 meters above the floor for 15 seconds. So here's my pineapple. I don't know how to draw a pineapple, but I'll try. There's my pineapple. Pretty good, right? Something like that. It's being held, just holding it, right? It's not being lifted or anything. I'm just holding my pineapple. How much work is being done on the pineapple? So we've got work, which is force times the distance. There's no force that actually ends up happening here because you're already just holding it. And then the distance is 1.2 meters above the floor. But because I'm just holding it, your work is actually being done on your muscles now. And that's stated up here as well. If you're just holding something, you're not actually lifting it up or anything, you're just holding it. There's no work actually being done on it. So since there's no actual distance covered to move it, that means there's no work that happens. So it's 0 joules for the work that's done. The last two examples, we've got a 5 kilogram banana box which is being pulled 11 meters along a level surface. So mass, distance. If the rope makes an angle with the floor of 35 degrees and the tension is 90 newtons, how much work is done on the box? So we're going to draw our box here. And we have a rope that's pulling up on the box at 35 degrees. So it's going to look something like that. And we have tension of 90 newtons. And the mass of this box is 50 kilograms. So this is our tension. We have a normal force which is acting on the box, force of gravity, probably a force of friction. And we're going to have some applied force as well, which we can figure out using our angle and the tension. And because this is being pulled, so it's probably got a horizontal distance of 11 meters, we're going to want to find the force applied for the horizontal component. So I'm just going to redraw my triangle over here. So we've got 90, 35 degrees. And we've got a horizontal component, which is like your x component, because your x-axis, and then a vertical one, which is like a y component. So depending on the direction in which you're actually pulling this box, so because this one is being pulled horizontally, we want to use the horizontal, the f of x component. If this box was being pulled up, then it would be different because then you would be wanting to use the vertical component. So let's find our horizontal one, or the f of x. So this is our adjacent, opposite, and hypotenuse. So we're going to use the trig SOHCAHTOA. And I'm going to use cos. So I'm going to do cos of 35, which is adjacent over hypotenuse, to find my f of x, which is my adjacent side. So multiply these two together. So my f of x turns out to be cos 35 times 90, which is 74 newtons. I'm running out of room. So you want to use the component of the force that's in the direction of the displacement. So now let's find work. Let's just do this down here. Work is going to be force times distance. And because this is a horizontal force, it's going to be my x component times my distance. So I found that to be 74 newtons times 11 meters. And that turns out to be 814 joules. So we had to use the angle of the rope to find the applied force for horizontal, times it by the distance of it being moved, and then it gave us the work. We've got 1385 kilogram car traveling at 61 kilometers an hour, brought to a stop while skidding 42 meters. What's the work done on the car by the frictional force? So our car, we've got a normal force acting on the car, we've got a force of gravity acting on the car, our applied force, and our force of friction. Now, because this car is coming to a stop, the applied force is 0. And if we want to actually find how fast it's moving, like the acceleration, let's take our 61 kilometers an hour initial velocity. The final is going to be 0. We have distance. Acceleration, we don't know. We can divide this by 3.6 to get it into meters per second. Now, the reason why we want to actually find acceleration is because we want to use the frictional force to find the work that's being done. So when we go to do work, which is force times distance, we're going to do force of friction times our distance. Now, to get the force of friction, we have to go back and use that F net formula, which would mean applied force minus force of friction. And our F net is mass times acceleration. And this is 0 minus force of friction. So we actually have to find acceleration in order to actually find that force of friction. So I'm going to use this information here to find the acceleration with our initial velocity, final velocity, and we would get our acceleration using that formula. You would get negative 3.4 meters per second squared. And then to do force of friction, your mass times acceleration and that would give us our force of friction, which turns out to be 4,709 newtons. So work can be done and it can be negative if the force doing the work acts in the negative direction. So since our force of friction pulls back on the car, then it could be negative. So to do our work now, which is going to be force of friction times the distance, so that's going to be 4,709 newtons times our distance of 42 meters. And this turns out to be 2.0 times 10 to the 5 joules for work.